Section 1 Introduction. In recent times, we've seen significant progress in the fine-tuning of large language models, LLMs, like ChatGPT and GPT-4. These models are capable of interacting and following instructions in both language and images, a feat that is currently unique due to their closed-source nature. This has inspired other works such as Alpaca and LLaMA adapter to fine-tune the publicly available LLaMA into language instruction models using self-constructed data. Moreover, models like LLaMA and LLaMA adapter v2 have incorporated visual understanding capabilities into LLMs for image condition generation. However, the development of an LLM that can handle instructions from multiple modalities, such as text, image, audio, 3D point clouds, and video, is still a relatively unexplored area. In this paper, we introduce ImageBind-LLM, a multi-modality instruction following model. This model fine-tunes LLaMA using the joint embedding space in the pre-trained ImageBind. Unlike previous visual instruction models, ImageBind-LLM can respond to input instructions from multiple modalities, not just images. This shows its potential for extensibility and generalization. We use the image-aligned multimodality embedding space of ImageBind to fine-tune multimodality instruction. For an image caption pair, we first extract the global image feature using the frozen image encoder of ImageBind. We then use a learnable bind network for embedding transformation. The transformed image feature is added to the word tokens at all transformer layers in LLaMA, providing visual conditions to generate the corresponding textual caption. Our visual injection method is attention-free and simply weighted by a trainable zero initialized gating factor. This allows the instruction cues of ImageBind's multimodality embeddings to be progressively injected into LLaMA without disturbing the original language knowledge. After this vision language training, our ImageBind-LLM can follow instructions of various modalities by applying ImageBind for modality-specific encoding. For instructions in 3D domains, we use the pre-trained 3D encoder in PointBind to encode the input 3D point clouds. To address the modality discrepancy of image training and text, audio, 3D, video condition generation, we propose a training-free visual cache model for embedding enhancement during inference. This cache model contains millions of image features in the training datasets extracted by ImageBind, which improves text, audio, 3D, video embeddings by retrieving similar visual features. We evaluated the multimodality instruction following capabilities of ImageBind-LLM in various scenarios and observed consistently superior performance. In summary, our ImageBind-LLM has four main characteristics. 1. It can respond to general multimodality inputs, such as image, text, audio, 3D point clouds, video, and their embedding space arithmetic encoded by ImageBind and PointBind. 2. It has tuning efficiency. During training, we freeze the image encoder of ImageBind and fine-tune partial weights in LLaMA using parameter-efficient techniques. 3. It uses an attention-free zero initialized injection. Instead of incorporating new instruction cues by attention layers, we directly add the multimodality conditions with all word tokens of LLaMA. 4. It uses a cross-modality cache retrieval. To alleviate the modality discrepancy of training and inference, we introduce a visual cache model constructed by ImageBind extracted image features. In the realm of visual instruction models, enabling LLMs to perform visual understanding has gained significant attention. LLaMA adapter was the first to propose generating language responses conditioned on image inputs. Other models like LLaMA, GPT-4, and Otter have made efforts to produce high-quality vision language data for training. Our ImageBind-LLM takes a step forward by tuning a multimodality LLM conditioned on language questions with image, video, audio, and 3D point cloud input, allowing for widespread applications. Section Summary. In this section, the authors discuss the advancements in instruction tuning of large language models, LLMs, and the need for developing LLMs that can follow general multimodality instructions. They introduce a model called ImageBind-LLM, which fine-tunes the LLaMA model using a joint embedding space in the pre-trained ImageBind. This allows the ImageBind-LLM to respond to instructions of various modalities, such as text, image, audio, 3D point clouds, and video, indicating promising extensibility and generalization capacity. The model achieves this by leveraging vision-language data for multimodality instruction tuning and using a visual injection method that is attention-free and weighted by a trainable gating factor. Additionally, a training-free visual cache model is proposed for embedding enhancement during inference to improve language responses to multimodality instructions. Overall, the ImageBind-LLM exhibits four main characteristics: multimodality instructions, tuning efficiency, attention-free zero-initialized injection, and cross-modality cache retrieval. Section 2.2 Multi-modality Alignment. In this section, we'll be discussing the alignment of multiple modalities, a key area of research in both vision and language. This involves creating a shared space for embedding different modalities for cross-modality processing. Some models, like CLIP, Align, and Florence, use simple contrastive learning to align image and text pairs, which has shown promising results in zero-shot generalization performance. Other models, like Flamingo, Blip2, and Magic, use intermediate networks to connect pre-trained vision and language encoders. Audio Clip and Point Clip extend the embedding space of CLIP to include other modalities, such as audio and 3D point clouds. Recently, a model called ImageBind was proposed, which shares a single latent space with various modalities, including image, video, text, and audio. Inspired by ImageBind, PointBind blends 3D point cloud modalities into ImageBind, achieving impressive 3D zero-shot accuracy. In this paper, we're focusing on aligning the shared embedding space in ImageBind, PointBind with a model called LLaMA to enhance multimodality instruction following capacity. Another model, Panda-GPT, also aims to tune a multimodality language model based on ImageBind, but it doesn't support 3D point clouds as input. Instead, it uses a stronger language model, Vicuña. In contrast, our model, ImageBind-LLM, is still based on LLaMA and introduces a unique attention-free zero-initialized injection with cross-modality cache retrieval for better multimodality reasoning. Now, let's briefly revisit some prior works, including ImageBind, cache models, and LLaMA adapter. ImageBind proposes to connect 5 different modalities, namely text, audio, depth, thermal, and inertial measurement unit, IMU, all by image paired data. It uses a contrastive loss during pre-training, which clusters image features with other paired modalities and pushes away unpaired ones in the embedding space. This allows ImageBind to encode different modalities into aligned feature embeddings, which can then be used to extend existing vision language models to incorporate new modalities. LLaMA adapter is a fine-tuning method that transforms LLaMA into a language instruction model by only using 1.2 million parameters within 1 hour. It exhibits comparable performance to the fully fine-tuned Alpaca. LLaMA adapter v2 is proposed to attain superior visual instruction following capacity. It adopts a joint training paradigm for image, text, and language-only instruction data, and still features tuning efficiency by updating partial parameters in LLaMA. One of its core innovations is the zero-initialized attention mechanism. Cache models, on the other hand, can be used to store the features and labels of a training set, organizing them as a key-value database. During inference, the test sample serves as a query to retrieve from the keys and aggregate informative values via the key-query similarity. Cache models have been widely adopted to assist deep neural networks in language, 2D vision, and 3D point clouds. Finally, we propose ImageBind-LLM, a multimodality instruction model, which includes 2 training stages: vision-language pre-training on image caption data and multimodality instruction tuning on visual instruction data. We also propose cross-modality cache retrieval for enhanced inference. The overall training paradigm of ImageBind-LLM is shown in figure. Section Summary. Bridging different modalities in a joint embedding space is crucial for cross-modality processing. Several models, such as CLIP, Align, and Florence, use contrastive learning to align image and text pairs, while others like Audio Clip and Point Clip extend the embedding space to audio and 3D point clouds. Inspired by ImageBind, our approach focuses on aligning the shared embedding space in ImageBind, PointBind with LLaMA for multimodality instruction following capacity, introducing attention-free zero-initialized injection with cross-modality cache retrieval for better multimodality reasoning. Section 3.2.1 Vision Language Pre-training. In this section, we'll discuss our approach to vision language pre-training, focusing on our model, ImageBind-LLM. We've designed ImageBind to work specifically with images, so we only fine-tune our model, LLaMA, to generate language responses based on images encoded by ImageBind. This allows the model to understand instructions from other modalities through their respective ImageBind encoders. Our strategy is to use vision language data to fine-tune a multi-modality instruction model. We follow the LLaMA adapter v2 approach, which involves a two-stage training pipeline for ImageBind-LLM. The first stage uses large-scale image caption data to learn how to generate responses based on images. The second stage uses instruction following data to maintain the quality of long sentence generation. To illustrate how this works, let's consider an image caption pair. We first use ImageBind's frozen image encoder to extract the overall visual feature of the image. This visual feature is then transformed by a learnable network, which we call the bind network, and added to every word token in LLaMA. LLaMA, initialized in an attention-free zero-initialized manner, is then conditioned by the image and generates the given image caption. The bind network is designed to align the embedding space between ImageBind and LLaMA. It starts by encoding the global image feature into a specific dimensional space using ImageBind. This encoded feature is then transformed using a linear projection layer, which adjusts the feature to match the feature dimension of LLaMA. We then use a method inspired by the feed-forward network, FFN, in LLaMA, where we apply 3 projection blocks with RMS norm, CLU activation functions, and residual connections. Each block takes the output of the previous block as input and performs a specific calculation to produce the output for the next block. After going through the bind network, we get a transformed image feature that aligns the embedding space from ImageBind to LLaMA. Next, we introduce the attention-free zero-initialized injection method. With the encoded image feature, existing visual instruction methods like LLaMA adapter v2, LLaVA, and MINI-GPT-4 add it as a prefix to the word token sequence in LLaMA. They then use self-attention mechanisms in LLaMA's transformer blocks to incorporate visual knowledge. However, this approach can be computationally expensive and increase training difficulty. In our ImageBind-LLM, we use a simpler and more effective method. We directly add the image feature to every word token at all transformer layers of LLaMA, which fuses the visual conditions with the language knowledge in LLM. We also use a learnable gating factor initialized by 0 to control the level of integration. This gating factor can gradually increase during training, injecting more visual semantics into LLaMA and contributing to stable learning in the early training stage. In the next stage, multi-modality instruction tuning, we connect ImageBind and LLaMA with a bind network through large-scale image-text pre-training. This allows ImageBind-LLM to understand multimodal inputs like audio, video, and 3D point clouds, and generate language responses based on these inputs. Unlike LLaVA and MINI-GPT-4, which use a well-trained language instruction model as the base LLM, we use a non-instruction model, LLaMA. In the second training stage, we partially tune the parameters in LLaMA to equip it with instruction following ability, while keeping the multi-modality encoders of ImageBind and the bind network frozen. Section Summary. The authors propose a vision language pre-training approach called ImageBind-LLM, which leverages large-scale image caption data to train a language model that can generate captions conditioned on images. They introduce a bind network to align the embedding space between the image encoder and the language model, and use attention-free zero-initialized injection to fuse visual information with the language knowledge in the model. In the second training stage, they partially tune the language model to enable it to understand and generate language responses conditioned on multimodality inputs. Section: Parameter-efficient fine-tuning. We've developed a two-step training process for our model, which we call LLaMA. The first step involves training with a mix of language and visual instruction data. For language instruction data that doesn't come with images, we use a placeholder image filled with zeros. To keep the model's ability to understand different types of data, we fine-tune it using methods that don't require many parameters, such as low-rank adaptation, LoRa, and bias norm tuning. This involves adding a low-rank layer to each linear layer in the transformer, with the rank set to 16 by default. We also make all the normalization layers trainable and add a learnable bias term to the linear layers. All other modules' parameters are kept constant during training. The second step is to fine-tune the model using high-quality instruction data from MINIGPT-4. This helps to avoid the model making up objects that aren't present in the input data. MINIGPT-4 provides us with 3.5K image description data, which we use for further instruction tuning. This process only takes a few minutes. After these two steps, our model, ImageBind-LLM, can understand instructions from different types of data. We also propose a method to enhance the model's ability to understand different types of data by constructing a visual cache model using ImageBind. This involves using ImageBind to encode a subset of the training data and storing them in the cache model. For any new input, we use its ImageBind encoded feature to find the most similar visual keys from the cache model. We then use these keys to enhance the original feature, which improves the representation quality of other types of data and reduces their semantic gap to the images used for training. Our model can also be extended to other applications with some modifications. For example, it can be upgraded to understand instructions in both English and Chinese. This involves replacing the basic LLaMA model with a bilingual model and adding Chinese instruction data for joint instruction tuning. Even though we don't have Chinese visual instruction data for the first training stage, our bilingual model can still learn the alignment between Chinese, English, and other types of inputs, and can follow Chinese instructions based on other types of inputs. Section Summary. In the parameter-efficient fine-tuning stage, we use language and visual instruction data to train our model. To maintain the multi-modality understanding capacity, we employ parameter-efficient methods such as low-rank adaptation, LoRa, and bias norm tuning. Additionally, we introduce a high-quality instruction tuning stage using manually collected image description data to improve the model's ability to follow instructions accurately. After fine-tuning, our ImageBind-LLM model can understand instructions with various modalities. We propose a cache retrieval method to enhance the multi-modality embeddings during inference. By utilizing a cache model of image features, we can retrieve similar visual keys and aggregate their values to improve the representation quality of other modalities. Furthermore, our ImageBind-LLM model can be extended to bilingual instruction following by replacing the basic language model with a bilingual one and adding Chinese instruction data for joint tuning. Despite the lack of direct Chinese visual instruction data, our model can still effectively follow Chinese instructions conditioned on other modality inputs. Section 3.3.2 Any-to-Any Generation. We're currently working on enhancing multimodality instruction models. At present, these models can only generate text responses. They lack the ability to respond with other types of outputs, such as images, audio, or point clouds. However, we're developing a system called ImageBind, which is an extension of CLIP. This system allows us to add CLIP-conditioned generative models to ImageBind's encoders. These models include Stable Diffusion for image generation, Make-an-Audio for audio generation, and ClipForge for point cloud generation. Instead of directly feeding ImageBind features into these generative models, we use a method called cache-enhanced generation. This helps to bridge the gap between different modalities, a technique similar to the one used in cache-enhanced inference. This way, we can create instruction models that can generate any type of response to any type of instruction. For instance, our ImageBind-LLM can generate both text and image responses to multimodal inputs like images, audio, and point clouds. Visual instruction models can answer questions based on the overall content of input images. But they struggle to link the text response with specific objects in the image. This is crucial for detailed tasks like visual reasoning and grounding. To solve this, we found a way to connect ImageBind-LLM with object detectors. When ImageBind-LLM generates a response, we use traditional noun parsers or ChatGPT to identify the nouns in the response. We then feed the input image and these identified nouns into object detectors to get object detection results. ImageBind-LLM was initially designed as a single-turn multimodality instruction model. But we've transformed it into a multi-turn chatbot by training it on multi-turn conversation data. This includes language conversation data from ShareGPT and visual conversation data from LLaMA. As a result, ImageBind-LLM can now be used as a multi-turn chat model to answer open-ended questions on multimodal inputs. In addition to following multimodal instructions, ImageBind-LLM also has the potential to control various APIs for multimodal tool usage. To achieve this, we've used the tool-related instruction dataset from GPT-4 tools to equip ImageBind-LLM with the ability to effectively use various tools. After training ImageBind-LLM on the GPT-4 tools dataset using our proposed training method, we've seen its impressive ability to call different APIs. This enables it to perform a wide variety of tasks, even when faced with tools it hasn't seen before. This proficiency in API control shows the potential of ImageBind-LLM as a versatile visual assistant that can solve a wide range of real-world problems.